So once we have the graph of our basic logarithm function, and this was the repeat right over here, this is the graph of y equals logarithm base 2 of x, y equals logarithm base 2 of x, right, for both of these. Let's look at some shifts. And we already know a few basics. For example, every single time that we have a graph and we add or subtract some number to the outside of that function, right? Remember that the rule went like this. A vertical shift always occurred whenever we added some number to the outside of the function, right? So if we said some constant plus or minus the function f of x, that will be a vertical shift. And on the other hand, our horizontal shift, side to side, is going to occur anytime we change the argument within the function by some amount c. So f of x plus or minus some number would be our horizontal shift. So looking at our two functions right here, if I have the log y equals 1 plus logarithm base 2 of x, what that means is that I'm going to take my basic function y equals logarithm base 2 of x and shift it up by 1. All the x values are going to remain the same. So on my original graph, this graph passes the point 1, 0. If I shift upward, I know that my new graph will pass to the point 1, 1. This is base 2, so this was a logarithm base 2 of 2 would be 1. Therefore, if I add 1 to my y value, we go up 1 to the point y equals 3. Likewise, at x equals 4, we would have found that y was equal to 2, so now y is equal to 3. Instead of passing through the point 8, 3, it would have passed through the point 8, 4. Instead of passing through the point negative 1, 1/2, it'll pass through the point 0, 1/2, and so on down the line. And graphing this new function right here, I'll do my best to sort of stick with the curve right here. I see exactly what's happening. My new curve, g of x, is the kind of function that looks just like the original function f of x, except shifted upward at every single point by 1. How about this guy right over here? Let's take a look at h of x. h of x says shift the logarithm to the right by 2. So what does that mean? Well, in this case, we are actually going to have to move a few features on this graph. Every single point on the graph, of course, that we have, this expression here says to shift to the right by 2. Right? Remember, when we subtract, you think, well, what value of x would make this function equal to 0, this expression equal to 0? We say positive 2, so that means we shift to the right by 2 at every point. So instead of passing through the point 1, 0, as the original graph would do, I would pass through the point 3, 0. Instead of passing through the point 2, 1, I would pass through the point 4, 1. Instead of passing through the point 4, 2, I would pass through the point 4, 6, and so on down the line. Now, a couple other things. I always like to identify what happens at the 1/2 mark at halfway between 2 and 3. Well, I know at the halfway between 0 and 1, so at 1/2 I would get negative 1. So 1/2 to the right by 2 is going to give me this. And remembering that my vertical asymptote in my unchanged function was at x equals 0, because I shift to the right 2, my horizontal asymptote also shifts to the right by 2. So it becomes x equals 2 instead of x equals 0. So I'm going to go ahead and dash in my line right here for my vertical asymptote. And if I'm graphing my shifted graph, it should look something similar to this, where it comes along that vertical asymptote, passes through these points, at each point 2 to the right of the original graph. I get this new function right here for h of x. Okay. So using a shift in translation always corresponds to exactly what we've done in the past, and remembering that what we're doing is we're just taking points and changing the x value. Now we can change all of these together. We can also get reflections and stretches and so on. and sometimes we will have to deal with that.